and welcome to section 9.2. So in today's lectures, we're going to be talking about pH. Right, so in the last section, we talked about acids and bases, and in general, like what they do, right? Acids give away a proton, bases accept a proton. We have like strong acids, which completely give away like every possible acidic proton, like completely dissociate. Weak acids don't so much. And now we're going to quantify that distinction with pH. So pH is a quantitative measure of the concentration of the hydronium ions in aqueous solution. And remember, H3O plus is technically what we have in solution with an H plus hydrogen ion attaching to water to make H3O plus. So sometimes you'll see it just as H plus, and sometimes it'll be H3O plus, and you can kind of think of those as the same thing. Okay, so this is pH is the measure of the strength of the acid or base character of a substance. So we always want to measure things, right? We want like a number in science class as much as we want qualitative things as well. Um, and so we saw something like this before as well, and now these numbers have to do with pH, right? Or they are pH, I should say. So this is like the physiological pH, like blood pH, the range that's normal, 7.35 to 7.45. And if pH goes down, that becomes more acidic, right? And so there's more hydronium in solution, but the pH is getting smaller. And when we get to actually calculating pH, you'll see why that is. But for now, the key takeaway, right? Low pH is more acidic, right? Low pH is more acidic. And so if you have a patient whose blood pH or something goes down, that's called acidosis, right? Which has the word acid in it, right? And there's only a small range at which acidosis is the diagnosis, and beyond that is just death. Like you actually cannot survive if your blood pH gets below 6.8. And at the high end, right, higher pH means less acidic, or it also means more basic, right? Acids and bases are kind of like the two ends of the seesaw, right? Or the two ends of the spectrum. The yin and the yang, the seesaw might be a good way to think of it, right? So if it's more basic, it's less acidic. And at high pH, it's less acidic, so it's more basic. And another word for base sometimes is alkaline. So like this is called alkalosis, and up to about the point of 8 pH, and then we can no longer survive. So this is the measure of pH. That's what this number is. You may be familiar that pure water has a pH of 7. So notice what is normal physiological pH relative to water? Is it slightly acidic or is it slightly basic relative to water? Well, it's above 7, right? So that means that it's more basic. So physiological pH is actually slightly basic above pure 7, pure water 7 pH. Here's some other body fluids and the normal pH range. And the only one that's really way different than about 7 is gastric fluid, which is a really low pH. That's HCl, right? So that's the acid in your stomach. The rest of these kind of hover around 7, right? Here we see blood as the physiological pH. Muscle cells and saliva are, well, I guess saliva has a large range that centers on 7, but muscle cells are slightly acidic. Urine has a large range. Saliva has a large range. Interstitial fluid is just kind of like blood, and intracellular fluid is acidic. Okay, so you don't have to, memorize these or anything, right? But it's good to have a reference in mind when you encounter like a pH value, right? So um, pure water is 7, physiological pH is about 7.4, and so then you can have that kind of reference in your mind and where these all fall. And notice none of them are very far from 7, except gastric fluid, of course. Okay, so now let's get to that 7 number and where all this comes from. To do so, we're going to talk about just pure water. Okay, so remember that water is amphoteric. And what does that mean? That means that it acts as both an acid and a base. So it can donate a proton and it can also accept a proton. So imagine what would happen when you have just water, right? Pure water puts water and water together in an acid-base reaction. Well, if one of the water molecules acts as an acid and one can act as a base, then you can actually see there would actually be a chemical reaction, which seems kind of funny because it's just water, but this happens automatically. And here is the actual reaction, right? So water plus water, but one will donate a proton, one will accept the proton, and then we end up with an OH minus and hydronium. Remember, this is what we measure to get pH. Okay, this reaction is always happening anytime water is. Okay, this is called the auto-ionization of water. And if we take a moment to think about that word, it might make sense, right? Ionization, right? It's producing ions. You have a negative and a plus ion, hydroxide and hydronium are polyatomic ions. And it's the auto-ionization of water, like it happens automatically without some outside molecule or something. Okay, it doesn't happen very much. Most water stays water, but it definitely happens, right? So very few water molecules react with other water molecules to produce hydronium ions and hydroxide ions. This always occurs and is always true no matter what. Now, like it says, very few. There's actually a equilibrium expression for this. See the equilibrium sign? Remember we had equilibrium constants? Equilibrium constants were kind of like products over reactants. And if they were greater than, if KEQ, equilibrium constant, was greater than 1, then you would expect more products. If it was less than 1, you would expect very little product and mostly reactant. And here, water has a special KEQ called KW, and it is equal to 1 times 10 to the negative 14. So that's very small. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's the size of KW. And that's equal to the product of the two ion concentrations. And so with a little bit of math here, right, you basically just take the square root of that number because these are equal to each other. And the concentrations of each of these are 1 times 10 to the negative 7 molar, very small, right? That's just measured, really. And then we get KW, and it's equal to this constant for a given temperature, right? So the product here, I'll try to highlight the important things here on this page. One of them is here. KW is equal to the product of the two concentrations, and KW is called the ion product constant. So this gives us some information, and eventually it will give us pH. But let's see first when we have the product of these two values is equal to a constant. So imagine, one of these values goes up by a factor of 2, the other must go down by a factor of 2. One of them gets 10 times bigger, the other one must get 10 times smaller. They're inversely proportional to each other, right? So, for example, when hydronium increases, hydroxide must decrease. When hydronium decreases, hydroxide must increase. And so before, when I said acid and base are like two ends of a seesaw, this is why, right? Is another reason why, right? Because hydroxide represents a base, hydronium represents an acid. So, if acid goes down, the base characteristic goes up. If the acid characteristic goes up, the base characteristic goes down, okay? And that's kind of qualitative, right? So here's the actual equations. We start with Kw, it's a constant, and it's equal to this product, and then here's the value that it's equal to. So if we wanted to solve for each of these concentrations, right, we can divide by the other one. So OH minus hydroxide concentration would be 1 times 10 to the minus 14 divided by the concentration of hydronium. And if you wanted to find the concentration of hydronium, knowing the concentration of hydroxide, it would be 1 times 10 to the negative 14 divided by the concentration of hydroxide. Right, so there's clearly like a relationship between these two numbers, and we see that here in this table. Given, if you're looking at, say, the hydronium column, if you know the concentrations of any of these, you always can find the concentration of the hydroxides. Here's a little trick to notice with the exponents, right? And this is just because of what we're doing to the numbers. We're taking the division and multiplication of them. What do the exponents add up to? So the exponents would be these numbers here. If we pick any pair, right? The sum of the exponents is always equal to negative 14. And that's the same as the negative 14 that comes here. So unless if, as long as the first numbers are just ones and we keep it simple for ourselves for now, then it's always true that the exponents add up to negative 14. And remember, these are negative exponents. So just another quick note about that. For example, 1 times 10 to the negative 5 is kind of like saying 1 over 1 times 10 to the 5. So it's a very small number, right? These are all very small. And the bigger the negative exponent, the smaller the number. For example, 1 times 10 to the negative 10 is less than 1 times 10 to the negative 7. Right? Okay. Let's do a question and then we'll end part 1 today. Okay, so what is the hydroxide ion concentration for an aqueous solution with a hydronium ion concentration of 1 times 10 to the negative 3? Okay, so first we can look at the ion product constant in that equation. Right, we're solving for hydroxide, but H3O plus is known, so we can divide both sides by that, which gives us OH minus alone equal to 1 times 10 to the negative 14 over H3O plus. Plug in the value that we have, and it's 1 times 10 to the negative 11. If you get pretty savvy at this, you could also see that negative 3 here what do we need to get to negative 14? Then we need negative 11 to get to negative 14, and you can get your answer. Now, I only recommend doing that if you understand the size of these numbers, if you understand the exponents and the negative and just how that all kind of works out. And if you can do it like this easily, then you can kind of skip ahead to the quick answer. Okay. What is the hydronium ion concentration for an aqueous solution with a hydroxide ion concentration of 1 times 10 to the negative 10? So the fact that the last question, we knew the hydronium and we were solving for hydroxide, and this time we know hydroxide and we're solving for hydronium, it doesn't really change the way we approach this question at all. So we start with the product constant, solve for the desired unknown, plug in what we know, and calculate 10 to the negative 4 molar. Here's a multiple choice question. Oops. There we go. Select the correct equation to calculate the hydronium ion concentration of a solution with a known hydroxide ion concentration. So what did we just do? You're solving for hydronium, and hydroxide is known. So what's the right equation? Answer for yourselves, and you get, hopefully, this one, right? A is tricky. It's the inverse, so it's not that. B is correct. And we'll do one more before we pause. What is the hydronium ion concentration for an aqueous solution with a hydroxide ion concentration of 10 to the negative 9? So you can set up the equation, you can solve it, you can maybe just look at exponents, and either way you get 1 times 10 to the negative 5. Okay, come back for part 2, and we'll talk more about the relationship between hydronium ion concentration and pH.